Welcome back, folks. Here's another example of flying by the seat of our pants doing circuit analysis. So I'm going to put another circuit up here, and we're going to try to apply as many laws and the knowledge that we have so far to find the values in the circuit we're interested in. So here's a problem that we're going to talk about now. And I want to find two things. I want to find the voltage across the 6K, and I want to find the voltage across the 3K. We might have to do this separately. Let's see what happens. Once again, I usually have you guide me through these problems so that we can hit some dead ends, screw some things up, break some things along the way, because that's the fun of doing this. But it's also not a great way to get to the right answer consistently. So let's have at it. So I'm going to look at this problem and I'm going to say, what do I need to do? Maybe I can simplify it. And it looks like that 4K and the 8K, I'm looking at these two over here, are in series. Okay, so let's start off immediately by saying these are in series. So I can combine them and I can say 4K plus 8K is 12K. Okay, that's a good start. And if I'm going to draw all of this, then, well, look, when I combine those, it's going to be in parallel with the 4K, right? So that series combination is in parallel with the 4K. Okay, so I'm going to end up with 4K in parallel with 12K. Pretty sure that's 3K, but don't trust yourself. Go ahead and pull out a calculator here, and let's do 4K in parallel with 12K. Can you imagine in 20 years if we're still using TI-84s? And these videos are still legit. Gosh, I hope not. 3K. Okay, so it is in fact 3K. Can't stand the 84. You all bought it because your high school teachers told you it was a good calculator. And it was for high school. You're not in high school anymore. But you still have it for some reason. Anyhow. Okay, so 3K, 3 kilo ohms if we combine all of that. Great. So let's redraw it and things will get simpler. But we have to kind of have some intuition that that's the first thing we should do. Okay, so come on. There we go. Get rid of that because it's the problem statement. We already stated it once. And as we redraw the circuit, right, we're going to remove everything that we've combined. And then we're going to connect the equivalent resistor in its place. So that parallel combination was connected to the right side of the 3K and this big bottom node that we have here. And we're going to connect that down here. Okay, so connect our equivalent resistor here. And that's going to be 3 kilo ohms. Okay, and that came from there. Okay, so hey, look, this looks a lot simpler. I like it. I like it a lot. What can we do with this? Well, if we want to find voltages across things, we might need to find the current through them. And, you know, these 3Ks, they're in series. They share this node exclusively. I could combine those. And if I combine those, then maybe we can get a little further along. Let's see how that looks. Let's do this again. And I'll try to, since I'm erasing a lot more this time, I'll get a little more aggressive with my method. Let's see. Let's cut out all of this. And let's tack on 3K and 3K. These are in series. My problem with this is that I lose this node, and I want to find the voltage across this 3K. So it's the voltage at this node in reference to that node. If I lose that node, then I'm going to have to step back at some point and figure out what's going on there. But let's say that that is a 6 kilo ohm. Okay, and the 3K is somewhere in there. It's somewhere in there, but we don't know. All right, getting better. Getting better. I can even get rid of that plus. All right, we can rearrange this. As long as we keep all of the nodes connected the way they are, we can swap these two. And we can end up with something we're a little more comfortable. Maybe you see it and you don't need to swap it right now. But as long as the same components are connected to the same nodes, we have an equivalent circuit. So if I swap those two things, and this is 1 milliamp, and this is 6K, and let's say this is the 6K that we want to find the voltage across. Okay, that might be useful. And then this is our other 6K. We have something that looks like the current divider. Okay, and we have a current divider that has equal branch resistances. So we count the number of branches and we divide the current by that. So we got two 6K branches. Each one is going to get 500 microamps. If you don't see that, that's okay. Apply the rule. Okay, give me the formula that you need in order to find that. I'm not looking for a voltage. Current divider finds a current, right? So we're going to find this, and we're going to call that I through the 6K that we're interested in. Okay. I 6K equals 1 milliamp. The opposite branch resistance is 6K, and the sum of the branch resistances is 6K plus 6K. Okay, and we end up finding that we have 500 microamps flowing through that resistor. That's pretty good. Okay, if I know the current through the resistor, I can find the voltage across it because I also know the resistance. And we can say the voltage across the 6K is the current through the 6K times, wait for it, 6K. Okay, and that's going to end up being, well, let's be careful with this. I believe it's 3 volts. Well, let's say it's 500 microamps. Okay, micro is E negative 6 times 6K, 6 times 10 to the third, and it ends up being 3 volts. Okay, so that's 3 volts. Okay, not bad. Not bad. I like that. What else we have? Well, we have the current. We kind of know the current flowing through here. Let's call this I 3K. I'm going to call it 3K, even though that's a 6K right there. But we got to remember that this is the series combination of 2 resistors. And one of those resistors, we want to know the voltage across. Okay, so we can go find that in the same way, and we're going to get this same result. It's going to be 1 milliamp times 6K over 6K plus 6K. It's split nice and evenly. 500 microamps. What if it didn't? Then we'd actually have to do some math, huh? Okay. And that current's flowing through this branch. And that branch is the same as this branch up here, this series combination. Right? So that's why I labeled it the current through the 3K. Because they're going to carry the same current. Okay? And we can find the current. We can find the voltage across the 3K if we just multiply the current through it by the resistance. All right. So we want to find the voltage across the 3K by taking the current through the 3K and multiplying by 3K. Okay. If we do that, we're going to find that it's 1.5 volts. Okay, so we'll go with blue. I was hoping for red. We got blue. We'll stick with it. There are the answers. I honestly don't care too much about what the answers are for this particular problem, but the path we took. Okay, we had to recognize we had some equivalent components that could make our lives easier. We had to do it again down here. We had to rearrange things so that it looked like the current divider that we know and love. We had to find the currents. Okay, so there's plenty of Ohm's law to be had in finding the currents and the definition of the current divider and things of that sort. And then ultimately we had to use those currents in the equivalent circuits and Ohm's law to get back to the values that we wanted in the first place. All pretty haphazard. You can get good at this. You can practice it. Some people are wonderful at doing this, okay, but it's not consistent, and it can be error prone. So we want to find a better way. Ultimately, after we practice this a little more, so more coming your way as far as the seat of the pants method of circuit analysis. Stay tuned and good luck.